just for some background, so Chiara did her PhD with Martin Pickering in Edinburgh. She then did a postdoc in Germany, in Saarbrücken University, then went back for another postdoc with Martin Pickering. He must have been good. And then she started an assistant professorship in Cardiff, and then most recently has joined Warwick University as associate professor, where she is still. And Chiara has a lot of research interests, from language production and comprehension to conversational turn-taking. First and second, where's the...
Oh, I think it's
it's
the creaky door.
First and second language acquisition, bilingualism, the role of motivation, curiosity, and surprise in language learning, and prediction in language learning as well. And so her more recent interest in language learning is also captured by her project that she's leading at the moment, a Leverhulme Trust project, which focuses on expectation violations as a mechanism for language learning as well. And then there's the usual. She's published all this excellent work in a lot of top-notch journals, including Psych Science, Cognition, Child Development, and so on. And what I particularly like about Chiara's work is that she combines psycholinguistic processing with a kind of joint action approach. And this is actually how we met as well. I think at one of the very early editions of the joint action meeting, many moons ago. But today, I understand from the abstract, you're talking about prediction and not so much the joint action angle, which is another really nice aspect of her work, is that she has strong focus on mechanistic explanations. And I think that's what we're going to hear about more today. Stephanie, can we change the ding dong thing on so that we don't hear it every time?
Yes, I'm on it.
Thank you. And then without further ado, over to you.
Right. Thank you very much, Judith, for that introduction. And I'm very happy to be here to talk to you about this work. So as Judith said, there's not going to be any joint action stuff in here and nothing to do with communication or conversation, but a lot to do with prediction. So I'm going to start with making clear what I do mean by prediction. And basically by prediction, I mean the pre-activation of linguistic representations before related bottom-up input is processed. And so this is the approach that we've taken in this review paper back in 2019 with Martin. But for today's talk, I'm also going to assume, which it's not something that we emphasize very much in that review paper, that these predictions are probabilistic in nature. And so that this pre-activation actually can be represented as a probability density function over possible representations. And for the purpose of illustration, I will assume that these representations that I'm talking about, over which we define a probability distribution, are words, but I think we could also think of them as features, or as long as there is some kind of network with nodes connected to each other, that probably works just as well. Okay, so by now I think most people would agree that prediction can explain many findings in language processing research. And the prediction is ubiquitous, by which I don't mean that prediction happens all the time. I mean that it can happen or occur at any level of linguistic representation. It can make use of pretty much any available cue that people have looked at. Both native speakers and second language speakers can do it. Both adults and children do it. And also, at least in native speakers and adults, can occur even when there is some cognitive load, when there's noise, when speech rate is fast, etc., etc. So where people still disagree, though, is whether prediction is a unitary mechanism. So essentially, is there just one kind of prediction mechanism that subserves language comprehension in all cases? And this question is somewhat related, although not totally overlapping, with the question of whether comprehension is fundamentally predictive. Some people believe it is, and some people believe the prediction is more like an add-on, or at least some forms of predictions are. That is not necessary for comprehension to occur. Alongside this debate, there is also another debate, which is about the relation between prediction on one end, so that's kind of during processing, during online processing of language, and memory and learning. So kind of the aftermath of prediction, as it has been called in some of the literature. And so I'm going to tell you exactly, what the debate is about and use some data from my own work to illustrate that debate. But before I go into that, I want to kind of tell you from the start what I'm going to try and suggest during this talk. And that is that essentially these two debates are related to each other and they both exist. And because prediction mechanisms change to adapt to different linguistic environments. And I'll spend the rest of the talk hopefully trying to convince you of this and explaining what I mean by prediction mechanism changing and also what I mean by different linguistic environments. Even if I don't convince you of this, I hope that at least this talk is going to be useful in highlighting that we should think about these two debates as being much more connected than they necessarily are in the literature, because these may suggest some new ways of resolving them and might help us identify some missing explanatory variables. So let's start with the first debate, which is whether prediction is a unitary mechanism. And here, the kind of empirical evidence that gives rise to the debate is the fact that sometimes incorrect predictions seem to lead to processing costs, and sometimes they seem to not lead to any processing cost. And I'm going to argue that in order to reconcile these potentially contradictory findings, we have to think about the precision of the evidence. And I'm going to explain what I mean by that. And then hopefully I'll also have time to go into the second debate, which I think is related. And here the debate emerges because sometimes we find that linguistic prediction errors seem to enhance memory encoding and learning, but sometimes they don't. And in this case, I think in order to reconcile these contradictory findings, we have to think about ideas surrounding uncertainty resolution and how that might be intrinsically rewarding for a comprehender or learner. So that's what I'm going to try and do in the next hour. Just to emphasize that basically, so I'm going to talk first about language processing, and everything that's about processing will be kind of marked with this pinkish color on the slides. And in that context, I'm going to talk about this debate about whether there are prediction costs or not. And then I'm also going to talk about learning, and that's going to be marked with this yellowish color. And in that context, I'm going to talk about prediction errors, because that's kind of the language that's used in that literature. And I mean, as I will be clear, as I've already suggested, I very much think that obviously processing and learning should be related, as in what happens during processing should be reflected in learning, and your learning should affect subsequent processing. And so just as another reminder, I'm going to argue that for processing, the missing variable is the precision of the evidence, and for learning is intrinsic reward. And if we don't start taking those variables into account, then we are unlikely to resolve this issue with contradictory findings. Cool. So having said all of that, let's dive into the first debate, which, as I said, relates to this question of whether there is a single predictive mechanisms or there are multiple different predictive mechanisms. And there is a spectrum here. This is just a collection of papers, but there's many more where people have engaged with this question and given very different answers. So on one end of the spectrum, you have maybe Hurtig and Money, where they really suggested that, prediction is something very, like an add-on to language comprehension. So it's not necessary for comprehension. Sometimes people do it, sometimes they don't, essentially. And on the other end of the spectrum, there's mainly Gina Cooperberg's work, where she really argues nowadays that comprehension is fundamentally predictive, and she, has produced some computational models of this idea to explain M400 effects as well. Cool. And now I'm going to try and explain how, this question of whether there is a single prediction mechanisms relates to the finding in the literature about whether this confirmed prediction incur a cost or not. So I'm going to use these sentences because these are the ones that we use in our studies. And in the studies that I'm going to talk about later, these sentences are always presented with pictures because it's a visual word paradigm. So, after you read Alfred's dog likes to chew on we not just assume, but we have known this, that the most likely alternative given, restricted number of options on the display is bone. But you also have the second most likely alternative, which is slippers, which is still somewhat plausible. And then we contrast this high constraint context with low constraint context, like now Craig is looking for where, any of the alternative on the screen is equally good. And the big question here is it harder to process slippers at the end of the high constraint context that makes a different word, namely bone, more predictable compared to at the end of the low constraint context that doesn't make any alternative more predictable than the others. Okay, so this question has been asked by many different people in the literature. Here, it's just a selection of studies just to illustrate, but people have, used very different methods from eye tracking, both, single sentences and corpus work, the visual word paradigm, ERPs, and essentially, most of the evidence seems to suggest that there are no costs. And then occasionally there is some indication that there may be some costs. Okay. So this has puzzled me for a while, not least because, as you will see, I found in my own work that sometimes there are costs and sometimes there aren't. But before I delve into the data, we should ask, why is it that we are expecting potentially this cost? In other words, should there be costs? And so Staub has got this very nice review recently of kind of the surprisal theory in language comprehension, where he makes it really clear, I just picked out this quote, that if you believe that essentially surprisal is a good theory for processing difficulty, then you wouldn't expect this cost because, as it says there, processing difficulty is determined entirely by a word's own conditional probability. So it doesn't matter whether there is another word that's more likely than that word. It really shouldn't matter mathematically. And similarly, this is from Gina Cooperberg's group. This is a computational paper where they develop a computational model of the N400 response within a sort of predictive coding framework. And again, they make the same point and they say, well, this fits very well with the evidence that the amplitude of the M400 is not affected by constraint. And so the idea is all that matters is the likelihood of the particular word I encounter, not of words that I could have encountered. Okay, so if you want to represent this graphically, this no-cost view suggests that, if we are interested in the probability of slippers, given our context, and essentially the view here is that the probability of slippers after a high constraint context or a low constraint context is essentially the same. And so it doesn't matter that the probability of bone is higher after the high constraint context than the low constraint context. Okay. However, there is also some indication in the literature, and this paper here is a paper that did speeded closed task, that sometimes it actually may be the case that the presence of a more predictable alternative changes the probability of a less expected word occurring. So graphically, we will represent it this way. So now in the high constraint context, the probability of slippers is not the same as after a low constraint context is actually lower. And that could be because of some form of competition between bone and slippers after a high constrained context. So in this case, we would expect costs. Okay, now, what people haven't talked about very much is that the reason why sometimes we find these costs and sometimes we don't find them could be, at least in principle, that maybe prediction is not a unitary mechanism, though maybe the nature of linguistic prediction, namely what happens to the probability of slippers in a high constraint context where bone is the most predictable alternative, could vary, right? It may vary from time to time, may vary for different comprehenders, it might vary in different contexts. And what I think is the problem is that most paradigms that have been used don't allow us to measure prediction and integration effects separately, because we tend to infer stuff about the nature of prediction, such as whether we have costs or not, from integration effects, such as inferential effects on the word after the target word is encountered. But if we use the visual word, it is possible to look at these two things separately. We can look at prediction and we can look at integration costs. And so that's what we did using the visual word paradigm with precisely the type of sentences that I mentioned, I showed you before. So now you can see the pictures as they appeared on the screen. What's important to emphasize here is that we created two sets of high constraint sentences. The top one that I called A biasing, because essentially makes the A picture, I mean, that's just an arbitrary label, the most predictable one, and another one for the same set of images, which makes the C picture the most likely. And slippers is kind of the mildly predictable second best alternative in both cases. And note that we never present the very unlikely and implausible completion after a high constraint context. And then we have the neutral sentences where any of the three pictures could be mentioned. So we did this both with children, and that's the data that's published in child development, and we also did it with adults. So I'll start with the kids. So this is a kind of complex graph, but it's a huge number of kids. And you can see the rows on this, there's a pointer. The top one is 2-year-olds, the middle one is 3-year-olds, and this is for 5-year-olds. And this is in the prediction window. So before they hear the final target word. And basically what you can see here is that, as we would expect, after A biasing context, they look more at the A picture, then a bit less at the B picture, and then even less at the C. After C biasing, that pattern is reversed, and after neutral, the lines are sort of on top of each other. What's relevant to say here is that what we called in the paper graded prediction ability, so kind of a measure of to what extent comprehenders distinguish both between the most predictable and the second most predictable picture, and they also distinguish between that and the really unpredictable one. So that ability seemed to increase with age. So the predictions became more graded as kids became older, or as their vocabulary increased. We couldn't really distinguish the two effects. But it's also the case that as kids got older, evidence for prediction costs increased. Okay, and so what you see here is looks to the slippers from the onset of the word slippers after a neutral context, that's the sort of orangey lines, or after a biasing context, that's the black lines. And you can see that, especially in the older kids, there is this delay after a biasing context, which we interpret as a cost. Now, here, we couldn't really tell whether the kids that were showing the prediction costs were also the kids that were showing the graded prediction. That was not possible to do. So, I mean, we don't know how the two abilities link to each other, but certainly we observe evidence for both. Then, as I mentioned, we also did this with adults, and this study is not published. And the reason it's not published is that we ran 2 experiments with adults, which are, you know, as far as I can tell, to the best of my ability, essentially, they're exactly identical, except that one has got a bit more items in it. But they reveal strikingly different results. So it's the same materials. In experiment 1, again, we replicate this graded pattern that sort of is reversed between the A biasing and C biasing sentences. This is for prediction. And there are no costs in adult. Now, if you just saw this, you thought, oh, maybe the kids have costs because, I don't know, they're still developing their revision skills or something like that. And so the adults just have graded predictions and no costs. That makes perfect sense. It's in line with surprisal. It's in line with Cooper's theory. Then we did a second experiment. Again, I said the same materials. It's participants from the same population, although different participants. And this time, we find that the predictions are not so graded. So actually, there is no statistical significant difference here. And there's no there. And now there are costs. Okay? So you see that looks to the slippers rise more quickly after the neutral context in blue than after either of the A biasing or C biasing context. So I'm going to put all of them together. So we have got one experiment at the top where we have graded prediction with no cost, and one essentially identical experiments where we have what you can call more serial or focused predictions. So they basically seem to focus just on the most likely alternative and costs. So what do we make of that? Now, what I'm going to suggest, oh, I realize I've drifted away from this microphone. So what I'm going to suggest is that one factor that we really have ignored in this line of research is the precision of the evidence. Okay, so now this concept of precision of the evidence comes from Bayesian theories of perception, but obviously there's also Bayesian theories of comprehension. And what I'm going to try and argue is that when the evidence is higher in precision, then the comprehender adopts a prediction mode that is more parallel. And this means that we observe no costs. And when the evidence is lower in precision, the comprehender adopts a more serial prediction mode that leads to somewhat larger, but still generally quite small costs. And I'm going to try and explain that with some figures, but first I need to explain what I mean by low precision or high precision of the evidence. And I think the best way to explain this is to contrast what's a prototypically low precision linguistic environment, you know, the classic cocktail party type of situation, with one that's prototypically high precision, which is just printed words. So the idea is that when you read a book, you know, the evidence is high precision because, you know, print is very high perceptual quality. The words are clearly separated from each other. Also, it's always available for revision. You can always go back. And further to that, you can also have some preview of the information that's coming next in the paraphobia. So within this type of context, I think it's kind of rational for a comprehender to not really commit strongly to any alternative, just predict a lot of possible alternatives in parallel, because they're going to be able to pick up some perceptual evidence that's going to, you know, prune most of them out and confirm one of them very, very quickly. And so it's like you can adopt this sort of wait and see strategy. And if you do that, your predictions are very parallel and you will see no cost. But you can't necessarily do that as a comprehender in this type of scenario. because obviously speech is transitory, so you can't easily go back, or you can't go back, essentially. There tends to be a lot more noise, so the quality of the signal is degraded. And I mean, even when there is no noise, speech is a much more variable signal. It's a lot, perceptually harder to process, I would claim. And essentially, you can't afford to use this wait and see strategy as much. Okay, so essentially what I'm suggest is that in most reading experiments, essentially, what people are likely to do is adopt this parallel prediction mode, where essentially the fact that you have, one alternative that's highly predicted, so this is your bone, say, doesn't have to mean that the pre-activation over sleepers is reduced. There is no competition, and then the evidence that comes in is high precision. But because essentially after a neutral context, the level of pre-activation of sleepers is the same. If you take the difference between these two probability distribution, it will in both cases result in the same amount of prediction error, which is not null, but probably small, and more importantly, similar across these two conditions, right? So when we compare them, we see no difference. And this is sort of inspired by this paper down here, which is actually talking about episodic memory, right? But that's where I got sort of the idea of this, representing it this way. Okay. Now, in at least some situations where the evidence is low precision, then you may adopt this serial prediction mode, in which case, after a high constraint context, so the level of pre-activation of sleepers is reduced here. And when you see this low precision evidence, that leads to a small prediction error. When you're after a neutral context, there is probably no prediction error at all. So if you compare these two, you will get some evidence for cost, but there will be very small costs. And what I'm arguing is that, if we really want to see evidence for very large costs, the contrast that we should look at, the maximal contrast, is between a situation where your predictions are serial and the evidence is high precision, because that will lead to a very large prediction error. So that compared to that, and a context where your predictions are parallel and the precision of the evidence is low, because that will be no prediction error. So that would be your maximal contrast. Now, I don't have time to go into explaining the detail of how I think we might create these contrasts experimentally, but I'm happy to talk about that during question time. Okay, now I'm going to move on to the second debate. So now we shift the focus from processing to learning. And so now I'm not going to talk about costs anymore. I'm going to talk about prediction errors, although, as I will say, they're probably, conceptually very related, if not the same thing, but that's kind of the language that's used in this area. And just asking whether it is the case that when linguistic prediction errors are larger, we see evidence of enhanced learning, or at least enhanced memory encoding. Okay, so this is very much a prediction that is made by many models. So there are around, this idea has been around for a long time, and it's called error-based learning. And it's the idea that essentially prediction errors computed during processing also explain learning. And relatedly, there is also quite a big literature, episodic memory literature, where the very same claim is made, right? That memory is driven by prediction error. Okay. So, again, I'm going to illustrate the sort of contradictory findings with my own work. So back in 2001, we had this paper published in Cognition, where we asked whether if we created a situation where we had higher prediction error, that would enhance word learning compared to situations where we have low prediction error. And the way we did it was like this. So if I show you these two objects and ask you to find the scheme, you would most likely apply what's known as the mutual exclusivity constraint. And so we infer that scheme, because it's a novel word, should refer to the novel object here for which you don't already have a word. And that's what both very young children, infants even, and adults tend to do. Now, the only difference in this paradigm is that we put the word scheme at the end of a sentence. And when the verb in the sentence is a constraining verb like eat, our assumption is that people will tend to look at the obviously edible thing on the display. In this case, it's the familiar object, the apple. And then when they hear the word scheme, they'll apply mutual exclusivity and revise that expectation and now think, oh, it's actually this novel object. In contrast, if you give them a low constraint sentence with the verb get, they should look 50-50 to either object before they hear the final word. And then when they hear scheme, then again, they'll map it onto the novel object. So that was kind of the design. So the assumption is the sentences with get will generate lower prediction error than the ones with eat. And the question is, will that lead to better memory for the association between the new word scheme and that particular novel object after a high prediction error sentence? Okay, so the way it worked, just to give you a bit more detail, is that we had the learning phase where we had 8 trials, half high constraint and half low constraint, plus some filler items where the familiar object was named. So the word at the end of the sentence would be apple, and just to keep encouraging people to predict the familiar object. And then people would have to tap on the object that they saw went with the word scheme. And then there was a very short break during which they did some filler task. And then there was an immediate retention test where they were just asked, tap the scheme. And then on the screen, they saw the target novel object and 2 other novel objects. Both of these they had seen before in the learning phase, but one was a target for a different trial, and one was presented on a filler trial. So it meant it was not named. They saw it, but it was not named. Whereas this one they saw and was named. Okay. We also did another version of this design for people that might be wondering, well, yeah, you might find better memory after the eat sentences than the get sentences, but that's just because eat is semantically richer, and so you just have more semantic cues that help retrieval. So we also did a version where the sentence was the same, it was always eat, but we manipulated the identity of the familiar object on the screen. So this is similar. Now note the novel object is different because we wanted to make it look more edible. So that's the plausible distractor condition because apple is edible. This is the implausible distractor condition because a car is not edible. So the idea is that here, attention should go straight to this novel object and there should be no prediction error. Okay. In practice, the 2 designs yield the same conclusions. Before I show you what they tell us, this is just a table showing that people did apply mutual exclusivity because most of the time they selected the novel object during the learning phase, but note that they didn't select it 100% of the time. And indeed, they were less likely to select it in the conditions that were eliciting higher prediction error. And we interpret this as evidence that, yeah, they were making the predictions that we wanted them to make, to the extent that sometimes they saw the scheme was another word for apple. This was a case for adults and was also the case for 2 to 4-year-olds. Now, in terms of the results of memory, so in this graph, we need to look only at these kind of part of the graph, because this is when the participants selected the novel or unfamiliar object as the target of the word scheme during learning. So I just said they did that most of the time, but not 100% of the time. So here we have a lot fewer observations. The error bars are larger. So we're going to focus on this and this bit. And basically, regardless of which design we use, the verb constraint or the object distractor manipulation, adults always show this prediction error effect. So their memory is better when they heard the novel word at the end of the sentences that generated higher prediction error. Kids never show any difference, and there is a significant difference between kids and adults. Okay. So again, based on this, you would conclude, okay, so prediction error, does benefit memory for new words, but maybe it's a mechanism that takes time to develop. So what we did then was trying to replicate this finding, well, conceptually replicate this design, at least with all the kids, to try and see, where in development this effect might occur. And so we did a version of the plausible or implausible distractor task. That was exactly the same material, but because the testing was taking place in Italy, everything was translated into Italian. So we had different pseudo words that, complied with Italian sort of phonological constraints and stuff. And this time we tested 4 to 10-year-olds, and again, adults. It was actually 2 different samples of adults, but here they're collapsed. And essentially what you can see here is that nothing. So there was a very, very small hint that in the kind of older children, maybe there was that effect, but because we didn't actually see this effect in adults, so again, remember, just look at this side of the graph. We didn't really know what to make of it. And we even did, like a massive combined analysis with the, English data and the Italian data for children across ages 2 to 10. And even then, there was only very, very, just anecdotal evidence for this effect. And anyway, we didn't replicate it in adults. So that was very puzzling. Now, when I got these findings, I started wondering, well, what could be behind this? And so I started looking into the episodic memory literature a bit more. And what you find in that literature is that, yes, it is true that highly unexpected information tends to be remembered better. But it's also true that very expected information is better remembered. And their explanation is that is congruent with your existing schemas. And so often what they find is actually some sort of U-shape, where at the extreme you have the highly expected and the highly unexpected, which both better than the unpredictable. And you say, okay, that's interesting. But then in the same literature, there's also evidence that sometimes it's an N-shape. So sometimes it's actually the unpredictable information is remembered better. And, and that, could be explained by the particular conditions under which this effect is tested. So just to, add to the puzzle, very recently my postdoc at Donnellan has collected some data on this paradigm, where we have a constraining context that's paired with either a predictable array or an unpredictable array. So essentially the difference is that the context is about playing music. So in this predictable array, you can anticipate very quickly that the final word is going to be ukulele. Whereas in the unpredictable array, you have got 2 musical instruments, and so you can't do that. You have to wait till you hear the final word. And then we have these 3 conditions. So either you hear the strongly expected word with a predictable array, So you expect ukulele, you get ukulele, or you have a strongly unexpected word, which, I mean, in this design is also very implausible. That's something to bear in mind. So you've got the constraining context with this array, and you hear whisk at the end. And then you've got this condition in the middle where you could, you know, it could either be trumpet or ukulele, and you get one or the other. Right. And so after they, go through this task, and their task is simply to, click on the image that's mentioned, then they get a recognition memory test. So they're simply asked to indicate their confidence that they've seen either the target image, so that would be the ukulele, or the distractor, so that's the other object on the screen. Or indeed, we also did this with the faces. That's why there was a face there, not showing this data here, but the pattern looks the same. And what you see clearly here is that there is some hint that the unexpected ones are remembered better than the expected ones. But also it's quite clear that the best memory is for the unpredictable case. And this pattern is particularly strong here, and it's also seen in the faces. So why would that be the case? I think in explaining that, the idea of reward is very useful. So if you think about it, the unpredictable trials are the one where the final word has got the higher information value, okay? And so it reduces the uncertainty about what the sentence is about the most compared to the other conditions. And the idea is that, the reduction of uncertainty is intrinsically rewarding. And there is a lot of evidence emerging that reward affects not just your procedural memory, so memory for, so actions and outcomes, but importantly, your declarative memory. And so one possibility to explain those puzzling results from our earlier paradigm, where sometimes we find a prediction error effect and sometimes we don't, is that perhaps by using these novel words, which have high information value because they're novel, then we are just, making everything quite highly intrinsically rewarding, and that might mask subtle differences related to the preceding context, potentially. Cool. So I think I'm probably going to stop there, so there is time for questions. Thank you.